Let's come on. Ah, there we go. Load. Okay. I feel like the snow just messed up my whole groove, you know? I mean, a part of me did not hate being at home, but then a part of me was like, I hate being at home. I mean, I still had to work too, so, you know, where did this go? Here it is. Okay. All righty. We're hitting on this now. Let me erase all this. Woo. Man, the work is never done. When you think you're done, you got more work. And then they're like, hey, you should be ahead. And I'm like, don't tell my brain that. I'm going to be waking up at 3 in the morning in an anxiety going, what? I'm not a month ahead? This isn't good. Freaking brains. Okay. So we were talking about molarity. Let's go back and practice doing some of those problems again. Yeah. Molarity. And then we're going to talk about freezing point depression and boiling point elevation. We're going to talk about all that today. Okay. Here we go. All right. So that website that I really like where you can get practice worksheets, stemsheets.com. They got science resources. You can pull up a molarity worksheet. You can just pick 10 problems. I'm going to generate that PDF. All right. So let's give this a go. We've got 112.3 grams. Let's do problems 1, 2, and 3. So some of these you're going to have to kind of have your polyatomic ion thing nearby and try to remember what those are. So ammonium chloride. Hello. Well, I'm glad you weren't in it. So we've got ammonium chloride. Remember, ammonium is a polyatomic ion. So be certain in your notes that you have a table of the polyatomic ions that you can go back and look at when you run into problems where they give you the name of the compound but not the formula. So make certain you got one of those. Also print you out a copy of the solubility rules. We're going to talk about that too a little bit. So let's do problems 1, 2, and 3. That's ammonium chloride. Calcium chloride looks like this. You should be able to write those on your own at this point because calcium is in group 2. So it's 2+, and chlorine is in group 7, 1 electron away, so Cl negative. All right, y'all remember how to do molarity problems? What's the molarity equation? Moles over liters. So if we're doing a molarity problem, okay. So for number 1, 112.3 grams of ammonium chloride are dissolved to make 1.250 milliliters of solution. All right, tell me what the molarity of that is. Remember, they're a trap. They're traps. Yep. You got to go grams to moles. and milliliters to liters, right? Anytime you see grams, what should you think? Molar mass, remember? If you at a chemistry rave and the DJ goes, if I say grams, you say molar mass, grams, molar mass, grams, molar mass, right? Molar mass every time. So, put a little star here. Anytime you see grams, molar mass. So let's do 1, 2, and 3, and then we'll check our answers. Miss Beavers took it because she doesn't have one, I think, in her class. And come to find out, it doesn't have the atomic numbers on it. I know, like the one thing you need from a periodic table. And it didn't have it. So I think I have some extra periodic tables just laying around. I mean, like for real, I do. You need one. You need one? Here you go. You're welcome. All right. Y'all ready to check your answers? You need them? No? Slow down, Miss Williams. Put on the brakes. They vary a little bit, but we're talking about just decimal variances. Yeah, use the Alex periodic table if you're doing the work in there. Is anybody in the library book club? If you are, they're doing lessons in chemistry this semester. And one of the days after they read the book, they get together and they talk about it. And on one of the days, I'm gonna do a lessons in chemistry demonstration where we make brownies. Because it's based on the story of a woman who wanted to teach chemistry, but people wouldn't let her because she's a woman. So she decided to teach chemistry through cooking. So all of the ladies in her area could learn chemistry through cooking. So we're gonna talk about the chemistry of brownies. That's gonna be fun. Cakey brownies versus fudgy brownies. Hmm. Yeah. 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 Oh yeah. Oh yeah. If you got a good working knowledge of chemistry, you can make a great marinade for a steak. All right. Let's have a look at the first 3 answers. No? Okay. This is what we got. How did y'all do? Okay. I can work through one of these. Let's work through one of these. Let's do, I guess we can do number 3. Well, yeah, let's do number 3. So we got 543.8 grams of calcium chloride, and I need to find the molarity of it. 543.8 grams. CaCl2. I need the molar mass for that. So I've got calcium and I've got chlorine. I've got one of these. I got two of these. Now I got to get the atomic mass. Periodic table right here. For calcium, 40.08, something like that. Chlorine, 35.45. Multiply these together and then add them up. Now, if you use your calculator, make certain you use order of operations. I mean, as far as like parentheses. Make certain you put stuff in parentheses, or it's going to do order of operations and mess you up. So we've got 35.45 times 2 plus 40.08. Okay. So I got 110.98 grams per mole. Is that what y'all got for the molar mass? This is for number 3. Did y'all get that? Oh, you. That's okay. That's all right. All right. So we've got this for our molar mass. I've got this here, and I'm making 1 liter of solution. Okay. So now we got to do a mole conversion. So I start out with grams. This is what I'm given, 543.8. And this is grams. I'm converting from grams to moles, right? So I know 1 mole, well, 1 mole is this many, 110.98, right? So I like to use this form, but if you like to use the fractions and the multiply and all that, that's fine too. I tend to just glaze over and freak out when I see lots of math sometimes. So this helps me keep my units in check. My plan goes on the top, grams to moles. So whatever my plan is, whatever I'm converting, I should see it in these boxes. Then I cancel out my grams. Then I just multiply across and divide by that 110. Either way is fine. Okay. Divided by. Okay. So I've got 4.89999. We'll just do that for now. This moles. So I got to ask myself if that makes sense. Well, if 1 mole is about 100, I got about 500. Yeah, that makes sense. That makes sense. This is almost 5. 5 times this would be 550. Okay, that makes sense. Now all I got to do, plug in my molarity equation. Molarity is equal to number of moles, 4.89, divided by 1. Oh, that's great. Is that what we got? Is that what the answer was? That feels weird. Yes, so I did 5 on the molarity. This is moles per liter. They went with 5 because of significant figures, right? 1, that should be 5. So that's how we do a molarity problem. Let's do something on molality. What's the difference between molarity and molality? Y'all remember? Yes. Y'all got it. Sound like multiple people got it. That's cool. Yes, so moles is essentially amount of stuff, right? Amount of particles, amount of molecules, atoms. A mole could be, we could have a mole of flowers, right? It's a lot of flowers. But yeah. So we've got amount of stuff divided by volume, right? Molality, this is amount of stuff over mass of stuff, right? This is amount of stuff over volume of stuff. Volume and mass are not the same thing, are they? They're not the same thing. So volume is how much space is taken up. Mass is how much stuff weighs, right? You okay? Were you up partying all night? You just you look sleepy, but I'm sleepy too, and I had a good night's sleep, so I don't know. I'm gonna pull up really quickly your book. I want to show you some things that you can do in your book that's actually pretty cool. It might be helpful for you. No, that was the wrong one. This one. Please wait. All right. Okay. So this is the section that we're on. Ah, I like this because you can go to the chapter that we're on. And if you're like, I don't want to read my textbook, do any of you actually enjoy reading a textbook? I mean, it's not riveting, you know. Maybe if I was trying to tell my organic students, like, can you imagine if we did organic chemistry but soap opera version? Because they use words like attack in organic chemistry. You know, you've got this nucleophile goes and attacks this carbon that's positively charged while it kicks bromine out the door. I mean, you could like come up with a whole story. Maybe if textbooks did that, that'd be interesting, but I don't particularly enjoy them. So I don't go, hey, I'm going to read this textbook today. So if you're like, I don't want to read all of this, I like the chapter summary. It just basically breaks down what each section covers. And it's a good way if you happen to find yourself that you learn this way. You can go through the different sections and compare it to the objectives and find where the information is that you might need a little extra work on and do that. Don't read your textbook front to back. I mean, you can, but you don't have to. So comparing the objectives to each section, you're like, okay, I want to work on some more molality stuff. Okay, section 13.3 is what we're doing with that. We'll be talking about colligative properties here in a second. Here's all of the different words that are super helpful. Here's our key equations. We're going to break these down. We're going to work on these two today. But I want to look at the practice problems. So we've got questions and problems. Let's look at molality. Let's see. All right, computational problems. Okay, let's look at 13.7. Keeping in mind this, we're going to do some molality problems. You're going to do similarity, but we're keeping in mind instead of the volume of the solution, we're looking at the mass. So let's have a look here. All right. Calculate the molality of each of the following solutions. So, first solution, we've got sucrose in water. So, how to do a molality problem? The first thing I ask is, what is it asking? So, what is it asking? We need molality of 30.2 grams of sucrose. I'm just going to write the formula C12H22O11. In 280 something, 85 grams of water. Right? Okay. I need the molality, so what's my plan? Well, I got to have the molality equation. It's usually a lowercase m with moles over kilograms water, right? Moles solute over kilograms of water. I go, okay. So I've got to use this equation. Now I got to look at my units. Can I just plug the numbers that are in there into this equation? Can't do that yet. So I've got to convert grams sucrose, moles sucrose, and I've got to convert grams water to kilograms water, right? Then I can take those numbers and plug it into my equation. So now I'm going to implement my plan. Got to do these two things first. Grams sucrose, molar mass, right? I'm going to write that over here. I've got a carbon, I've got a hydrogen, I've got an oxygen. I got 12 of these, 22 of these, and 11 of these. Is it 001 or just, I think it's 01. I think that's right. This is 1.008. I think this is 15.999, right? Got to multiply each of these individually, then add them up. What we got? Y'all got your calculators? Okay, I was just double checking my numbers. Okay. What y'all get for that molar mass? I'm going to write these out individually because I don't feel like typing the whole thing into my phone calculator. I have a nicer one than this. I don't know why I'm not using it. Okay. You had 300. $376. Okay. I'll compare it. So I got 342.285. Oh, okay. Okay. So we'll just, let's see. We'll just say 343. We'll just say that for now. Okay. There we go. 343. All right. So I put what I'm given, 30.2 grams. I'm converting from grams to moles. And then I put my molar mass here. That's 1. Cancel out those units. 30.2 divided by 343. I got 0.088 moles. Is that what y'all got? Yes. Okay. 0. Yeah. Yes, that's fine. Okay. Now I got the moles. Now I've got to convert grams to kilograms. I can just move the decimal place. If you're like, I forgot how to do that, just remember King Henry doesn't usually drink chocolate milk, or King Henry doesn't usually do crystal meth. Whichever one, it don't matter. Whatever you can remember, that's the goal. So U is unit, and I'm going from grams to kilograms. So I'm going to move 1, 2, 3 decimal places to the left. 1, 2, 3, 0.285 kilograms, right? So now I just do my molality equation. Divided by 0.285, which I'll get. So I got 0.31 or 0.309, we could say that. And that's moles per kilograms. Let's see. Well, we'll look at the others in a second. I want you guys to do the second one, and then we'll check our answers. You can do the same type of process if you like, and then we'll check our answers. Yes. We're doing 13.7. So 8.35 moles of ethylene glycol. That's C2H6O2 in 1905 grams. You can do the same type of setup. If you want, you can do something different. What's up? You can approximate, that's fine. Yep. Okay, I'm gonna press the answer button up there. And we're gonna get to see how close we are. Y'all ready? Hold on, okay.
No, when I say I mean just class.
It's okay. Ooh. So they already gave us our moles for ethylene glycol, so we don't have to do any mole conversions on that, so that's cool. The only conversion we got to do is grams to kilograms, right? Do you need the molar mass for the water for this problem? No.
I didn't.
That's right. Yeah.
So what I did
Yeah, that's another way to do it too. That's all fine too. There's multiple ways to do the thing to get to the answer. Use the one that works best with your head. So, all right, let's check our answers. Okay, yeah. How did y'all do? 4.38. Okay. We get stuck. Okay. Depends on, yeah, it's all right. So 8.35 divided by 1.905. Yeah. Okay. So the lowercase m is molality, capital M is molarity. All righty. Let's talk, we'll get back to this in a minute. Let's talk a bit about colligative properties because we need to discuss that. Okay. Alrighty. Colligative properties. We're going to write these out here. So that's what the lab is this week, based on colligative properties. All right. So we were out for snow, right? Some of us rejoiced. If you happen to live in Memphis, then you were at the mercy of MLG&W. Oh my goodness. All right. What would you expect to see with a city? What would they do to the roads? They knew ice was coming. Salt. Memphis doesn't always do that. You would salt the roads, right? Some might even use kitty litter because sometimes salt can affect concrete. Why though? Opposite of that. It lowers the freezing point. So colligative properties, essentially what this means is adding stuff and in this case, we call it a solute, to a solvent. Oftentimes we think about water, changes its behavior. And what we look at for this is freezing point, we also look at boiling point. It can also affect vapor pressure. We'll get to that probably next class. I want to look at mostly these two right here because we got math with this week. Freezing point and boiling point. So if we add stuff to water, it's going to change the freezing point of the water, and it's also going to change the boiling point of the water. Freezing point drops. Boiling point goes up. So if you add salt to an ice-covered sidewalk, or if you put it down before the ice gets there, you're making a solution of salt water. So you're lowering the freezing point, so it's going to have to get a lot colder for it to ice over. Does that make sense? Well, it's basically melts any ice that's there, so it lowers the freezing point. So it has to get a lot colder in order for it to freeze. Yes. So you would have to look at, the freezing point of water usually is like 0 degrees Celsius. So you'll have to look at how cold it gets to below freezing with water. Kind of the cool thing though is water that comes from the sky isn't just straight up water. There's other stuff in it too, right? So you already have other stuff in it. You might have some carbon dioxide. You might have a few other things, some other ions. We get acid rain, right? That's a whole thing. So you got other stuff in the rain. So you have to kind of determine what is it going to freeze at, and then you have to add the salt or the kitty litter or whatever appropriately. I don't know. I hadn't thought about it. I mean, I don't see why. You know. Yeah. You know, I don't know. I don't know that I would eat snow anymore with the amount of pollution that's out there. Snow cream. Did y'all ever make snow cream when you were kids? You take it, you put a little vanilla on there and some sugar. It's like an icy. Yeah, it's just no different than if you got an icy and put like a syrup on it, you know? Yeah, I mean, I don't think I would do that anymore. I know too much about pollution.
I'm sitting here like,
It's okay.
like I recognize the thing, but still.
Yeah. So, a little caveat on this, adding stuff to a solvent, adding solute to a solvent changes the behavior of the solvent, changes its behavior. And it being solvent, yes. Mhm. So we have rock salt that we use with the ice. It can get the ice kind of colder. It's a thermodynamics thing where the cold passes through a bit faster in the metal container and it can freeze the ice cream on the inside a bit faster. And the reason why people do that is because they can churn it while it's freezing. You just shoved it in your freezer, you can still do ice cream, but it's not going to be creamy. It might end up settling and get all flaky and stuff in parts. Yep, that's cool. So we've got our freezing point drops and our boiling point increases. The important thing about this is it doesn't matter. I'm going to make a little note here. It doesn't matter what the stuff is. It doesn't matter what the stuff is. It matters how much stuff you put in it, right? So it doesn't matter if it's kitty litter or salt. If you put stuff in water, it's going to act differently. And it depends on how much you put in there. So there is a video, I saw it on Facebook. Memphis is so funny. There was this little lady who was out in her bathrobe. She was walking down the street. I got you, Memphis, putting salt. Had a little salt shaker. Like, oh, you gonna need more than that. But adding the little bit of salt, probably not gonna do anything. So if she had like a big shaker, that'd be different, right? Mm. Yeah. Uh, yeah. How much stuff is important, not what it is. Well, I'm going to come over here now. Let's write out what that looks like. So, kind of going back to the difference between molarity and molality. How we measure the solute stays the same in that. It's in moles, right? The thing that changes between molarity and molality has to do with how we're representing the solvent. So with molarity, it's moles solute per liter solvent, right? Molality, which is the lowercase m, same thing, moles solute, this time mass of the solvent. So when we're determining freezing point depression and boiling point elevation, we have to look at amount of stuff in an amount of stuff, right? Mass, we can easily convert grams to moles, can't we? We can easily convert grams to moles. Can we easily convert liters to moles? No. We would need the density of the solution. Then we would have to convert liters to grams based on the density of the solvent, and then we could get the moles. This is what we use when we're dealing with colligative properties. Use for colligative properties. Because this gives me the amount of stuff that I have and an amount of solvent that I have. So this ratio of amount of solute into amount of solvent, this is the relationship that we look at and what we use for the math when we're trying to deal with freezing point depression and boiling point elevation. So let's look at those equations really quickly. Let me find that book. Here it is. Go to key equations. Here we go. So, okay, let's look at these really quickly. Before we start freaking out over letters, let's look at what's the same and what's different. We're going to compare and contrast between these two equations. Without even looking and trying to figure out what each word means or what each variable means, what's the same and what's different? Okay, K and the M is the same. Tangent T is the same. These are the only things that are different, that F and that B. What do you think F stands for? Freezing. It's a, yes, it has to do with the freezing point depression. B is for boiling point. Yep. So let's talk about the relationship between these. I gotta text my kid real fast. Okay. In class. All right. So I'm gonna erase right here. So we've got the change in temperature is equal to a constant times molality. That's the same thing between the two. So we've got change in temperature is equal to a constant times, I'll just do times molality. Then we remember that molality is equal to moles per kilograms. Now, this constant, we've got two different constants that we can use. We can use boiling point constant. We've also got the freezing point constant. Each solvent has a constant associated with the boiling point and a constant associated with the freezing point. That doesn't change. We give that to you. So if it's water, it's a specific number for each of these. You can look it up on a table, right? The change in temperature. This is what we observe in a lab, right? The molality, we also measure in a lab. So if we're making a solution, we need to know how much the water weighs, and we need to know how many moles of solute we've added to it. We can get those measurements in the lab. We can weigh out our solute, convert that to moles, right? Grams to mole conversion. However much you weigh out in a lab, you just use the molar mass and convert it to moles. You can get the mass of the water on the scale. Empty beaker, put water in it, measure it, subtract that number, right? Get your water mass. So we can get that in a lab. This we can get from a table, and this is what we observe. So the change in the temperature, this is the difference between the regular boiling point, or the regular freezing, we'll just say regular freezing point, freezing or boiling point. And then we've got minus the new freezing or boiling point. And we just, if you get a negative number, we just, get the absolute value. So we look at how did it change? This was what the freezing point was before I added stuff to it. And when I added stuff to it, it dropped. This is the new one. I subtract those two numbers, plug it into my equation. If it's boiling point, this was the boiling point before I added stuff to it. This is the new boiling point after I added stuff to it. Let me subtract those numbers, plug it in there. So it's the exact same equation for both of these, whether it's boiling point or freezing point. So in the lab this week, we're making solutions and we're testing to see what the freezing point is before we add the stuff. And then we look at the freezing point after we add the stuff and compare. Okay. There's one particular thing, the lab, that we have not talked about yet. It's called the Van't Hoff factor. And that freaks people out because it sounds scary. Yes. Let's just briefly talk about what it is. And it has to do with, ironically, interaction of water with different things. Let's talk about that briefly before we start doing some problems. It's 11:23. I'm going to have to eat my lunch really fast today if I remember to eat. All right. Van't Hoff factor. All it really means is, let me find a way to say this. Kind of, yeah. So, yeah. How well, that's a good one. Well, a solute dissolves, we'll just say in water, because that's where we look at this mostly. How well a solute dissolves in water. There's reasons. A associated with how well something dissolves in water. Largely has to do with how much water can interact with or play with a solute. Okay. So if water can interact really well with a particular thing, it's probably going to have a pretty high Van Hoff factor. Let me pull up a table really quickly. I'm going to kind of show you what I'm talking about. Let's go here. Okay, let's look at tables. There's usually a pretty decent, here we go. All right, here's an example. I just wanted the image. I don't want all that. I just want the image. Okay, here we go. Okay, so when we're looking at Van Hoff factor in general, what we're doing is looking at the ability for water to be able to interact with a particular compound. So, looking at sodium chloride, I'm going to just write it this way. When it dissolves in water, it looks a bit like this. NaCl negative, right? It separates into two individual ions. So, if I put a salt crystal in water, how many things can water play with? Here. 2. Now, what does that mean? That means I've got an oxygen that's attracted to there. Hydrogen is attracted to that negative. So there's 2 different parts to this ionic compound that water can interact with. So if I was just spitballing it, I would say Van Hoff 2, right? But does everything work out the way we expect in a lab? No. Like magnesium sulfate. Magnesium sulfate looks like this. Even though the charges is where people get tripped up, like, oh, that's 4. No, it's not. This is one thing, and this is one thing. So I would expect it to be 2. But it's not when we measure it. It acts weird. So oftentimes when we're in the lab, when we start trying to figure out the Van Hoff factor, I know that's one of the components of the lab this week, it may not completely sync up the way that you would expect to find it. We're going to kind of see that a bit with sugar. So you'll be calculating your own Van Hoff factors in the lab. So just looking at it, why is this one 3, magnesium chloride? Yep, there you go. 3 places for water to play with. Yep, that's fine too. So the goal here is, can you look and see how many atoms are there for water to play around with? I don't make people do a lot of Van Hoff factor stuff on a test or anything. I would just tell you if it has a Van Hoff factor. So how that works into here, we'll put it here. And it looks like the letter I. For a lot of intents and purposes within the textbook, they just assume it's 1. But But if it's something other than 1, we usually just tell you. Usually just let you know. Okay, how are we doing with this? All right, let's see if we can work one of the problems. Okay. Okay. Where was it? It was questions and problems. Okay. Let's go to freezing point depression, boiling point elevation. Let's see. Hold on. Nope, that's not it. We will be getting to vapor pressure and the rest of that this week in osmosis. Okay. Almost. We're almost there. Let's see. Nope, that's vapor pressure. I'm trying to find. Okay. What are the boiling benzene? An aqueous solution. Okay, here we go. Let's do 13.63. An aqueous solution contains the amino acid glycine. Assuming that the acid does not ionize in water, calculate the molality of the solution if it freezes at 1.1 degrees Celsius. So we only see one number here and we freak out, right? What are we supposed to do with just one number? Okay. I'm going to erase this. We're going to use this formula here. We're going to do this step by step. And the first thing we got to do when we're looking at this is go, what is it asking? Molality. It's asking for the molality of something. We're like, and then this scares everybody. But remember, colligative properties have nothing to do with the identity of the thing, just how much stuff, right? All right. So, what is it asking? Molality of a solution. We're just going to start there. I need the molality of the solution. What does it give me? Gave me a freezing point, right? Gave me freezing point negative 1.1 degrees Celsius. And I've got a solute in water, right? So what is the freezing point of water usually? 0, right? So I can make a little note here. Freezing point of water is 0 degrees Celsius. So what's my change in temperature? 1.1, right? So I've got my change in temperatures here. So let me make a note. I'm going to use colors. This right here is my delta T, right? That's my delta T. So I'm going, all right, I need to know the molality of a solution. I'm given a delta T. That means I need the molality equation. Well, I'll need that. Well, hold on. I'll need the freezing point depression equation. Kf times molality. So that's my delta T. I need to know what this is. And this is a constant, right? Now I'm going through. I've got this. I don't know what the heck this is yet. But I can look up this number. right here on the table, right? Woo! I'm going to write on myself. Okay. Let me look that up. What is the KF of water? 1.86. You'll have to use kilograms. 1.86. All right. So on the internet, we looked it up. KF equals 1.86 kilograms, moles. Wait, is it? Kilograms times moles divided by temperature. Is that it? Okay. Is that right? I don't know. I might have that written wrong. I don't want to write it wrong. Degrees Celsius. Okay. All right. So now I've got this number. I've got this number. It's 1.1. I can just plug these in and find out what the molality is. So we've got 1.1 is equal to 1.86 times M. Now it doesn't feel so bad. All right. 1.86, 1.86. So what's the molality? What? .5913. Let me go back to our problem. There we go. The change in temperature, you're going to want to take the absolute value of it. So whenever you do your subtraction there, you got to take the absolute value because you can't have a negative molality, right? That doesn't make sense. So it's just the number difference between the freezing point before and after, boiling point before and after. Right. Right. You don't want to have a negative number here. So what are the steps that we did? First of all, we identified what it's asking, because that's really important when you look at a problem like that and you're like, oh my God, amino acid, and then you like check out for a second. When you come back to Earth, go, okay, what is it asking? In this case, they wanted the molality of the solution. The next thing I did is I go, okay, what information does it have? Well, if I see a freezing point or I see a boiling point, I'm probably going to be using this equation right here. If it has to do with a freezing point or a boiling point, I'm going to be using this equation right here. And then it's not so bad because then I got a constant. And if I got one of these other numbers, I'm going to be cool, right? We're just talking about a little simple division at that point. So the majority of work in one of these problems is figuring out what it's asking. Usually it'll say probably one of the last sentences in a giant problem. Y'all know that trick where you look at the bottom, you read the problem, and then you're like, okay, I'm freaking out. Look at the bottom again and see if you can find what the actual question is, right? So if you're one of those people that freak out reading halfway through a problem, look at the bottom first, see what it's asking, then go back into the problem and see what it gives you. Look for the numbers. What are those numbers? Freezing point, boiling point. Okay, probably don't need this. So that'll be a good solid plan when you work in problems like this. Potential traps, making certain that you check your units on your constants. Not likely you'll find this in grams per mole, but just pay attention. This is in Kelvin, wrong number. You got to have Celsius, right? So that's going to be your potential traps. Okay, we have like 6 minutes left. Let's see what's coming up, what we're going to do next. We're going to finish up this chapter this week. So use this as your checklist, these learning outcomes. We're going to do osmotic pressure, and we're going to talk about vapor pressure. We're going to talk about movement of water. We've already talked a little bit about Henry's law, but vapor pressure is also a colligative property. We're going to talk about that. So on Thursday, we're going to knock the rest of this out. Okay. Well, do you guys, let's see. So we're knocking out module 1, module 2. I got to go through and write out module 3. Let me look at do I have like a course calendar on here? I don't know if I did that. I don't think I did. Well, do you guys want to how do you guys want to test? Do you want to, do I have it in the syllabus? Did I write it in here? I have like 4 or 5 different preps, y'all. Stuff is hard. I try to keep up with it on this way. Let me see. Let me keep going. Yeah, I don't have it listed on here. Okay, so how about, do you guys want to take we can do like in class chapter tests. Do you want to do a test on, I think it's 12, 13, and I think the next one we're going to do is thermodynamics. Do y'all want to do one test on all of that? Or do you want to do a test just on 12 and 13? What y'all want to do? Yeah, it wouldn't be, it would just be divided up into chapters. I know your midterms are in March, right? Okay, so we'll do like 2 chapters at a time. So once we knock this out, then we'll put it in the books to do a test. What you think? Okay, that works. Let me shut this off.